Today what we're going to talk about is some of the mistakes that I see, some of the common mistakes that I see students in my classes make with SystemVerilog. So over the years is that students make sort of a common set of mistakes in SystemVerilog. And it's related to just some of the, I don't know if it's confusing syntax, but are not obvious syntax that I see in some of the SystemVerilog constructs. So what I'm going to do is I'm going to talk about, I'll do sort of a little lecture and a little bit of showing how this works with the EDA Playground, which is a tool that Doulos has to help let you test things out, okay, on your own. So I'm going to start off with wire assignments, okay? And so what you'll notice is that in SystemVerilog designs, that in the old days in Verilog there was basically a wire and a reg, okay? A wire was used to connect between component instances. It was used to, a signal that needed multiple drivers, let's say. And so it was common use, especially when you had hierarchy in your design. And the reg was effectively used for local variable storage. But the name is kind of a misnomer, because by the fact that it's a reg, you might think that it actually generates a register when you synthesize the design, but it's not always the case. It could just be a wire, depending on how it's used. Anyway, to get around the confusion in SystemVerilog, the term reg, or the construct reg, has sort of been deprecated. And so what's being used now is the term logic, which is effectively the same as reg, although it's a little confusing because logic can also represent the data type, which is the 4-state 01xz. So what I see people do is that they may take a design which has wires in it and regs in it, and maybe want to convert it to logic, because one of the other nuances is that with SystemVerilog, you don't necessarily need wires except for special cases, because the logic type, as opposed to the reg type, can be assigned to one time, so you can do a point-to-point connection. You can even do a connection across component instantiations, which was not the case in Verilog. In Verilog, you had to use a wire. So by effectively limiting the usage, the need for wires, especially if you're doing synthesizable designs where you don't use tri-states or you don't use wired kinds of connections, tri-state kind of connections, the need for a wire dissipates pretty rapidly. So what a lot of folks then will try to do is use logic, and that works fine, except that there was the case with the wire assignment, which was kind of special, in that if I have a wire here X, okay, and it equals A and B, this actually creates the wire and assigns the value continuously. So if A changes or B changes, the value of X is updated continuously. All right, as opposed to the reg, where the value of A and B here would only be assigned at the initialization time. After that, it would be whatever the next assignment was. And so since you can use a logic effectively as a wire for a point-to-point connection, okay, you might think that the same kind of thing happens, but it doesn't. Okay, where it acts like a wire. It basically acts like a reg in that if you create, in this case, logic Y, and we assign it to be A and B, it creates the variable and assigns the value once. Okay, so that if you want to emulate the wire behavior, what you actually have to do is create the variable, in this case logic Z, okay, and then you have to do a continuous assignment to Z, which is legal, in SystemVerilog because you can do one assignment to a variable in this case. All right. So just for completeness, let's go ahead and actually look at this example then using using our EDA playground. Okay, so here I've got the actual design loaded into EDA Playground. And if you haven't seen EDA Playground, basically it allows you to do SystemVerilog, Verilog, VHDL, etc. designs here. And then you can pick your tool. In this case, we're using the all-deck tools, but there are other tools available. And then there's, of course, compile and runtime options that you can specify on the left-hand side here. Now, the way that an EDA Playground design typically looks is that there is the test bench code on the sort of the left pane here, and then there's the design code on the right. Okay. Now, in our case, since this is such a tiny little design, what I did was I just created the design with a couple of signals that I have in an always block to generate effectively the stimulus for the design. So I don't really need two files. And in fact, that's what it would do is if you actually use both panes, it effectively, it's as if you had two files in your design. Okay, so once I get my code specified here, and so you can see I've got, again, the always block that does the A and the B assignment, but I've also have this initial block so that I can dump out a VCD file, and this is the sort of the style is how you create it. Anyway, I'm going to dump the VCD file out so we can actually see the waveform display. So if I go ahead and run this, what it'll do is it'll run the simulator, it'll compile, run the simulator, and then it'll bring up the waveform display. And so now we can see that A is changing basically A is changing, B is changing. They're off by 10 in this case. All right. And now if we look at signal R in this case, which was the, go back here, signal R is the reg, well, it got initialized to the initial values of A and B, which is 0. So sure enough, it's 0 all the time. And the same thing happens with Y, which is the logic signal. Okay, initialized to 0, and then it just stays 0 all the time. Whereas you see the wire assignment, which was X, okay, wire assignment X here, effectively, whenever A and B are a 1 at the same time, it's a 1. Okay, and you can also see that Z, the signal, with the assign, the variable logic, with the assign works the same thing as the wire assignment. So again, if you want the signal to be just initialized, of course you can just assign it like this. But if you really do want it to act like the old wire assignments worked in the past, you need to create the variable, but then assign to the variable as well. Let's continue on with some other examples here. The next thing I wanted to do was compare static versus automatic variables and static versus automatic tasks, because this is something that's pretty confusing to some of the students. Basically, in this case, I've got an always block with a static int, okay, which static, by the way, is a default. So this is really a redundant word, if you want to call it that is static. And the idea behind static is that it retains its value from whenever the always block is run. In other words, the first time it comes into at compile time, this particular count is going to be initialized to 8, and then as the always block runs, it'll update it or not, or just use it. But the point is that the value remains constant as the always block runs. Okay. Then we've got another one. The second one here is we've declared count to be an automatic variable, which means that every time the always block starts up again, okay, the variable count will get initialized to the value 8. and then we can modify it as necessary later in the always block, but once it actually comes back around again, it'll get initialized to 8. And then finally, this is normal. Again, static is actually the default. So in this case, count is declared as a static int, but it's not initialized. And so it'll start out at, well, the default value of int is 0. So it'll start out at 0, and it'll remain, well, in this case, we assigned it to 8. But again, it maintains its value from invocation to basically when the always block runs. All right, fine. So that's the variable static, but there's also a static and automatic tasks. And what these do is that if you have a static task, which again is the default, then any variables in the task itself are also going to be static. So I, in this case, is going to be a static variable. Now this has a different connotation within the task context, because what it really means is that if you call task st multiple times from, let's say, multiple always blocks or multiple initial blocks, every one of those invocations of st, they share the same variable I. So if one invocation updates I, that updated value will be seen by the other one when it runs. Okay, and I'll show you an example of this in EDA Playground here in a second. So that can be sort of non-intuitive when you're trying to, let's say, reuse a task over and over again, to do some common operation. Now, if you don't want that behavior to happen, what you can do is you can set a particular variable to be automatic, and that means that every invocation of st, in this case, will have its own copy of variable j. Okay, so that it's not shared among the different calls. Now, if you have an automatic task, that means that all of the variables are automatic by default. So in this case, the variable I in every invocation of at, in this case, will be unique. They'll have their own copy. But now j, since it's static, will be shared among all of the at invocations. All right, so let's. One other thing is that this is just kind of bringing home the point. This is the example that we're actually going to look at in the EDA Playground example. So what I've got is I've got a task called test, TST. It's got an input A and an output Y. Okay, and it's got a static int x, which we reset to 0. Okay, which of course is the default value anyway. Anyway, so then in the invocation of the task, we're going to say x gets a plus x. Okay, so whatever the a value is. And then we're going to just say y gets a. And then we'll basically write the two values out. So the point is I want to show you what's going to happen. Because what I'm going to do is I'm going to run it first as a static variable. And then I'll run it again as an automatic variable. And then the idea is that we're going to have two concurrent initial blocks. So both of these are running concurrently in the simulator. And then we're going to be calling the test task, from each of those, and they're going to be at the same time. So the question is which one is going to be invoked first? That's really tool dependent. The point is that these two tasks are actually called at time 5. Okay, but we don't know the order. And then we wait 20 and we'll call them again. So anyway, this is an example of calling the same task from multiple processes. So an initial block is a process, and then we'll watch the variable actually get shared between these when they're static, and differently when they're automatic. Okay, so let's run the. So I'm going to select the static variable case. So again, we've got our task test, input A, output Y, and x. We're going to have a static int x, which gets us set to 0, and then we'll do the y gets a plus x. X gets a plus x, and y gets a. And again, we've got our two initial blocks that are going to be running this code. So if I run this using the x as being static, so it's shared between the two calls, what you'll see is that it looks like it runs this one first, test of 100. Okay, so x gets to be 100, and yeah, y is 100, so that's what a is. Then it runs the other one, which, okay, fine. So it ran the 100 first, then it ran the 50. And you can see that x retained the value from the first invocation because it's already at 100, so that when we add the 50, now it's basically 150. All right, then we wait for 20, and it looks like, okay, again, it ran the first initial block. So here's 500. It ran that. So we've got 150 plus 500 is 650, and then it ran the second one down here. We add another 300. All right, so you can see that the value of x is actually shared between all the different calls, such that when it gets updated, then successive calls use that updated value. So just for fun here, let's change this to automatic, and then we'll rerun it again. All right, so now what's going to happen is that you can see that this call to test and this call to test, okay, so again, the first one seems like it ran first, and so x gets to be 100, okay, but this call, when it runs down here at the bottom, it starts with x being 0, so because it's got its own copy of the variable x, because it's automatic. And so now you can see that the x value does not increment because it's not shared. Anyway, the point is that if you want variables to sort of be shared across these different tasks, which is probably not that common, maybe for some things, then you can leave them static. But if you really want them to have their own unique value, then you need to make them automatic. In this case, we've got a task called avar that has an input val and an output outv. And then we've got two variables that are declared outside of the task. So effectively, these two variables are global to the task. And they're actually even visible to the task because they're in the same scoping. All right, so within avar, you can actually access glob B, and you could do other V, but what we're going to be doing instead is we're going to call avar down here, and the output of the task, the output variable here, is going to be other V. Now, what is a little different about this is that you might think that when variables are assigned immediately or is assigned in a task, that things happen immediately. But what's going to go on here is that when we actually assign to glob v here in the variable, in the task, the value val here is going to be assigned to glob v immediately when it hits this statement. Okay, and so it'll happen at with no delay when we call avar down here. Now, after 10. The internal variable outv here, this is just local to the task, will actually be updated, but the output other v here will not be updated until the end of the task. And so sometimes that can actually confuse you if you'd think that when the outv is assigned, right here, that immediately it's reflected on the output variable here. But what actually happens, as I was just saying, is that the output variable outv here is not actually reflected in other v, the output, until the end of the task is reached, which is going to be 10 after this assignment actually happens. So let's look at this in EDA Playground. Okay, so here we have our code again, where we've got the global variable, we've got the other variable, we've got our task, which has got our input, val, output, out v, and again we've got our assignments with the pound 10 delays in there. And then what I've done is I've actually created an initial block that's going to call avar with 37, which is decimal. So we're going to see the radix on the waveforms is hex. But anyway, and then we're going to say avar with 73. Okay, so we're just going to run basically two calls in this thing. So now if we run this, it will basically we're going to, okay, here we go. So we can see that at time 0 we get 25, and sure enough, if we look at when this task is actually called right here, okay, this one right here, then it would be at time 0 because there's no pound delay, there's no delay, and because glob v here is assigned as the first thing in the task, it gets set immediately to the value 37 again, which is 25 hex. All right, but when does the assignment to out v happen? Because theoretically, after 10 it assigns to the output value, but then it waits another 10 before it actually ends the task. So let's see. So sure enough, out v, which is the internal variable, gets set after 10, but the return value doesn't actually happen until 25. Okay, and then we can see the same thing happening for when we change the value to 73, which again is 49 hex. Yeah, so as you can see, the assigning to global variables happens immediately as soon as it's running the task, but output values, or the output, any variables that are assigned as output parameters don't actually get updated until the task actually ends. Okay? All right, so let's continue on with some other examples that we'll see. So in this case, enumerated type. So basically, this is an enumerated type. We've got idle, we've got start, we've got stop. So these are the legal values of a variable called state, which is an enumerated type. So of course, you can say if state equals idle, then do something. Set state equal to start, for instance. And so state can only have these values: idle, start, and stop. Now the nice thing about enumerated types is that you can use them for state machines. You can use them for any kind of control system, let's say, where you want to be able to label or name certain values with a readable name. It makes your code a lot more easier to read. And the best way to use them is actually to use a type def like this. So you say type def enum idle start stop, again the values, and you give it a name of the type such that I can declare variable state now to be of state type. So this is a very common way to use the enumerated types, and it works really well. Now if you go to print out a enumerated type, by the way, if you put these in waveforms, you will see the value of being displayed as idle, start, and stop. So when you're debugging your state machine, it's great because you can see it's in idle, it's in start state, it's in stop state. Now, if you print those enumerated type values out, though, it doesn't actually print out the state name, the name of the state, okay, or the name of the enumerated type value, unless you do something. You basically have to pull a little trick on it, or you have to use basically a enumerated type conversion. Anyway, so what in this case, what do we got? We have signal. We got red, green, blue is our color type. Okay, and then we declare a sig1 as being of that color type, and we initialize it to be the color blue. Okay, fine. So this is a legal enumerated type, and this is, again, we're using a type def. Now, if we want to print this out, if we just do a $display of signal1 like this, or sig1, the problem is that it won't actually print red, green, and blue. What it'll print is what's called the ordinal value, because each of these enumerated type values has a number associated with them. So red is 0, blue is 1, and green is 2. So that if you just print out sig1 like this, you're going to get the ordinal value. Effectively valued. What numeric value does this value represent, as opposed to what you would like to see, of course, which is the actual enumerated type value. So the way you can do that is you basically say sig1.name, and now since sig1 is of enumerated type, it'll actually get the value converted into the enumerated type, and then you'll be able to see it actually printed out as red, green, blue, as opposed to the. Now there are some tools. This is not common, but there are some tools that allow you to sort of format it using a string. But again, this is sort of non-standard usage, I would say. The right way to do it is actually to use the name, use the enumerated type function that gives you the name. All right, so let's go ahead and try this out in our EDA playground again. So here's our little example. We've got our again, our type red, green, blue, red, blue, green in this case. We've got a signal of type of that type, and it's initialized to blue. And so when we run this, okay, what we're going to see is that, okay, so the first print out is this one right here, and sure enough, signal 1 is equal to a 1, because the ordinal value of blue, 0, 1, 2, blue is 1, and so we see 1, which is probably not what we want. So again, if we use the name, okay, sig1.name here, sure enough, we now get blue. Okay, and as I said, it's tool dependent whether or not you format it as a string. You get it. In this case, well, we see that it is not. It basically does it. It follows the standard and actually uses. So basically, you're required to use the name attribute. Okay, so let's go ahead and continue on. Structs. So these are common data structures that are used to hold complex types. The value of a struct is that you can basically associate a number of different types of fields together in one object. So, for instance, you're trying to do something that uses an IP packet. Instead of having a bunch of arrays with names that sort of represent the different fields and data fields and all that kind of stuff, it's which you had to do in the old days with Verilog. In SystemVerilog, what you can do is you can just declare something as type struct. In this case, S is a variable of type struct, and it has a bit field called B, an int field called I, and an 8-bit logic field called B. And so you can individually set those by saying s.b is 1, so it sets the bit. s.i is -8, it sets the int. And s.v is 8 tick hff, so it's 8 bits of ff sets to v. Fine. Now, the way that you actually set all of the values in one shot is you use something called an assignment pattern like this. So in this case, the little tick mark in front of the curly braces, because curly braces, if you remember, is a concatenation. It concatenates all the bits together. And so that's not the same as writing to the individual fields, and I'll show you an example in a second. Whereas if you use the little tick mark, it basically says assign 1 to the first field, -8 to the second field, and ff to the third field. That's what the assignment pattern basically says. And the way you get an assignment pattern is you need the little tick mark at the very beginning there. So let's look at, for instance, this, where we've got a packed struct now, which has a logic A. It has a short int B. Okay, so this is 1 bit. This is 16 bits. And so if we just say S gets the concatenation of 1 bit and 16 bits, a 1 here and zeros here, this will actually work, because with a packed struct, A and B are contiguous, they're next to each other, and because this is 17 bits and this is 17 bits, that works, okay? But that's kind of a unique case. Because if you did it like this, where we concatenated a 1 and a 1, well, what's the problem here? This is only 2 bits, right? And so it'll basically, this 2-bit value, because S is 17, this 2-bit value will get extended out to 17 bits, and the two ones will end up in B and not in A. Now to solve that, what you do is you just put in that, again, you make an assignment pattern, and so now this lower value will go into the lower field and the higher value will go into the higher field. And so now it works because of the assignment pattern. And if you want to be even more descriptive, what you can do, instead of relying on the order of the fields, you can actually use the key value. That's what A and B are here. These are the key values, and now you can put these in any order. Okay? And again, you need to use the assignment pattern to actually make it work. Okay, so let's go ahead and look at this using EDA Playground. All right? So what we have, again, is we have our struct, pack struct here, OS, and we've got a logic A and a short int B, and we're going to run it again with using the 17-bit value, which again will work just because it's 17 bits. Then we'll run it again using the 2-bit value and show you it doesn't work. And then finally using the assignment pattern for the last two. Okay? So if we go ahead and run this, what we'll see is that, again, the first one will work because we got lucky. The second one, all right, so here we go. So you'll notice we're using the %p here to print this out because that gives us it's basically a pretty print for it's basically a pretty print for the structure. Okay, it works with any of the arrays or structs or any of that, those kinds of more complicated types. So in this case, okay, we set S to be 1 with 16 bits of zeros. Sure enough, A is a 1, B is a 0. And again, here's the one that fails because we say S gets 1, B, basically this is a 2-bit concatenation. Okay, so sure enough, B gets 3, that's the 2 bits, and what will happen is then it'll take those 2 bits, add 15 zeros to it, and so A gets to be a 0. Now it does work again when we use this method with the assignment pattern. Okay, because again it'll split this into the 2 field initializations such that A gets 1, B gets 1, and then finally the last one works again, and the only difference here is we're just using these keys to specify what the different fields are. And again, I could put these in a different order and it would still work. The next mistake I want to talk about is the equality operators. So if you look at the different equality operators in SystemVerilog, there's the double equals, the exclamation point equal. So this one, the double equals logical equality, the other one is inequality, not equals. And then there's also triple versions of these. The difference between these two is that the double equals really only checks for zeros and ones. So if you've got 0 and x or x and 0, then you get an unknown value, which is okay for logical kinds of things, but it doesn't really work as what you'd like to do for, let's say, something like checking the output of your design in a test bench. So that's where you would use something like the triple equals and the exclamation point double equal here to do, because what you're really getting is an exact matching function. You're always going to get either it exactly matches or it doesn't match. And so the result is never unknown, because the problem with the unknown is that you can have a situation where you try to do an action on the fact that you're testing, for instance, let's say we're testing vectors. This is the very common one where if you look at the double equals, if it's 0, 0, 1, 1, 0, 1, 1, 0, they're not the same. Obvious. But in this case, it's 0011, and then it's 0xx1. It could be the same. We don't know, because we don't know what these x's are. So the result of the double equals in this case is going to be unknown. And if you have a output checker like this, if, let's say, the output from the design is not equal to the expected output, which is going to come from, golden reference model, golden files, whatever it is. The point is that if you use the not equal version of this, and you end up with a situation like this one, the one we talked about, 0011, 0xx1, the result of that is going to be unknown, and so it won't display the error. So even though the design is not putting out the correct, as far as we can tell, is not putting out the correct output, we won't actually get the error message. So if we change it to not the exclamation point double equals in this case, the case equality version of it, now the fact that the design is generating x's and the golden vectors do not have x's, this will actually fail and write out your error message. So again, we can actually look at this in our EDA playground. Okay, so here I've got A is 0, B is 0, A is 1, B is 1, and over time. And the one to look at is this one right here, where even though they're exactly the same, we got XX, 1, 1, zeros here, and the same over here. Down at the bottom, I've got I've got an always block that's sensitive to A and B, and I use if A equals B, and then if triple equals B. And you'll see the difference. So if I run this, what you're going to see is that where they're both equal for 0, 0, for 1, 1, so 0, 0, 1, 1, that's just fine. And then for the vector compare, where they're equal, it also compares. But you can see that the one with the x's here only compares on this line right here for the one with the triple equals. So if it's there is no, it doesn't compare at all on the double equals, because the value, the result of the comparison is actually an unknown, and so it doesn't trigger the if statement to actually do the dollar display in this case. All right, so